Hi, everybody. This is our video on a calculus introduction into physics. In this video, we're going to talk about what calculus means graphically for our position, velocity, and acceleration. So we'll start right off here. Calculus meet physics. An object moves along the x-axis according to the equation x of t equals 3t squared minus 2t plus 3 meters. Use the equation to determine the instantaneous velocity at t equals 2 and t equals 3. Use the equation to determine the time that the object changes direction. And use the equation to determine the equation for instantaneous acceleration. So, excuse me. What we will do is we will start using what's called the power rule. Now, the power rule is something that you guys may have heard of. I think ASCII supposedly taught you guys the power rule. But the power rule is the basic way to take a derivative. So we will start with the derivative of 3t squared. So let's say this is, we'll call this a new function because it's not actually x of t. We'll call this f of t is 3t squared. The derivative is f of t, f prime of t, because we've taken the derivative. What you do is you take the exponent and multiply it by the coefficient that's out front. So 3 times 2 is 6. And then you still have your variable. And then your exponent gets decreased by 1. So this would be 6t to the first. So that is how you do the power rule for 3t squared. Now let's do the power rule for negative 2t. If your original function is negative 2t, then the derivative, f prime of t, you take the exponent, which is a 1, right? And you multiply that by negative 2, so you get negative 2, right? And then you decrease your exponent by 1. So that would be t to the 0. And what is anything to the 0 power? That would be 1, which means that you can exclude that, and your derivative would be negative 2. Okay? So that is the derivative of negative 2t using the power rule. Now, the derivative, if your f of t equals 3. To take the derivative of that, you would need a variable. Since there is no variable, the derivative is 0. No variable, no exponent, so f prime of t here would be 0. So, to find the instantaneous velocity, what we need first is we need a velocity function. So if we say that x prime of t is the derivative of x of t, then the derivative of position is velocity. Oh, that's bad. Oh, I can't erase in this program. Blame Google Slides. Need to redo this app. That's even worse. X prime of t equals v of t. Okay. So if you take the derivative of position, you get velocity. Now, if we take the derivative of 3t squared minus 2t plus 3, we already did that, right? We just did it in chunks. So x prime of t, the derivative of 3t squared is 6t. The derivative of negative 2t is negative 2. The derivative of 3 is 0. So that would be 6t minus 2. But we're taking the derivative with respect to the variable, which is time. Now, if you have more than one variable in a function, you can take the derivative with relative to one variable, and the other variables are not treated, and you don't take the derivative of their exponent and things like that. But we'll save that for another time. So we took the derivative with respect to time. So instead of meters being our new unit, it would be meter divided by the unit that we just took the derivative to, which would be seconds. So your velocity function, v of t, is 6t minus 2 meters per second. Okay. Now we need the instantaneous velocities at t equals 2 and t equals 3. So what they're really asking us to do is find v of 2 and v of 3. Okay. So to do that, we would plug in. Now I'll write our equation down here. V of t is 6t minus 2. So if we want v2, we would plug 2 in for t. 6 times 2 minus 2, that would be 12 minus 2. That would give you 10, right? 10 meters per second. I don't have enough room to write it, but imagine there's a unit there. Now, if we want v3, you plug in 3, so that'd be 6 times 3 minus 2, which would be 16 meters per second. So there you have it. V of 2. I'm going to get better at this writing, I promise. V of 2 is 10 meters per second, and V of 3 is 16 meters per second. That is your answer. You will get a lot more practice with the power rule. So if this is freaking you out, don't worry. The next video, we will just do some calculus prep, some calculus practice, and we will also look at some more practice for you guys to get accustomed to the power rule. In class, we usually have much longer to discuss this, and I usually have a couple more examples, but I'll work those in where I can. So that's the answer to A. Your instantaneous velocity is t equals 2. At t equals 2 and t equals 3 is 10 meters per second and 16 meters per second. So that means that this sucker is really moving. That's an acceleration right there, 6 meters per second in that 1 second. All right, so let's clear that out. Part B, the time that the object changes direction. Now, this is a preview of a really difficult problem in the Chapter 2 homework 2.2. What you need to do is you need to look for where an object changes direction. Now, if we have a velocity function, right? Velocity, v of t equals 6t minus 2. How would we know when an object changes direction? Just by looking at its position or its velocity function. Well, one way you can do that is look for where the velocity equals 0. If you start traveling at, let's say you start at a negative velocity, then your velocity has to hit 0 before you can turn around and change direction to go positive. Vice versa, if you're going positive with a positive velocity and you need to change direction, you need to decrease your velocity to 0 before you can go negative velocity and go backwards, right? So to change direction, you find where the velocity equals 0. Where do we do that, or how do we do that if we just have a velocity function? Well, if we want velocity to be 0, let's make it 0. So we will say 0 equals 6t minus 2, right? Solve for time, we need to know the time at which the velocity is 0. So you add 2, right? You got 2 equals 6t. That would need 1/3 equals time. So at 0.33 seconds, our object just changed direction. And if this is going a little too fast for you, pause it, ask a question in the discussion boards, or just go back and listen to the power rule all over again, because I know that was a very fast moving section. But to find where an object changes direction, you can look at where the velocity is 0. That almost always indicates a change in direction. Now, to check your work, you could look at the velocity at on both sides of this function. You can look at what is v of 0 and what is v of 1. You'll find that at v of 0, you're going to have a negative velocity, and at v equals 1, you will have a positive velocity. So you can tell that you will have a change in direction there because it was initially going backwards and then it turned to go forwards. All right, now part C, the equation for instantaneous acceleration. Now, how would we find acceleration if all we started with position? Well, like we talked about in the previous video, position is to velocity as velocity is to acceleration. So if you can take the derivative of position to get velocity, you should be able to take the derivative of velocity to get acceleration. So let's say we have v of t equals 6t minus 2. Acceleration with respect to time. You'd take the derivative of that. So what would be the derivative of 6t? Well, you imagine that there is a 1 up above that t. Multiply 6 by 1, you get 6. Then decrease the exponent of your t. That would give you t0. T to the 0 power is 1. So you would have 6 times 1, just 6. And the 2 has no variable, so it gets no derivative. So you'd have 6 plus 0. So your acceleration function is 6 meters per second squared. So the equation for instantaneous acceleration is 6 meters per second squared, which tells us that there was constant acceleration the whole way, right? It doesn't change because there is no t in the function. If there is a t, if that were 6t meters per second squared, then we know that for every second, that acceleration is changing, right? But since for the entire function, it is just 6 meters per second squared, then it is a constant acceleration. All right. And if that confused you, pause it, go to the discussion board, or watch the power rules section over again. Now for 2.09, calculating velocity from position graphs. Now, what physics property is represented by the slope? Now we're looking at a velocity graph. So this is the same velocity graph that we used last time. So what would be represented if we found the slope of this? Now, if we found the slope in the last video, that told us the acceleration, right? If we were able to find the slope of this graph. So if we have slope, that is your rise over your run. Rise is your change in y. Run is your change in x. So our y value is delta v. Our x value is delta t. Delta v over delta t, change in velocity over time, that is the definition of acceleration. So our slope would be acceleration. You can also see that would be in meters per second, which we can also call a meter per second squared, which is the standard unit for acceleration. So last time, in the last slide, we took the derivative of velocity to get acceleration. Here we can find the slope of velocity and also get acceleration. That's a connection we need to make, and we're going to make that over the next few minutes. Now, how do we analyze this graph to find displacement? So displacement can be found by going backwards, right? So we found the slope of the graph to get to acceleration. But what do we do to this graph to go the other way? We can go from position to velocity to acceleration. How do we go from velocity back to position? So what we can do is we can find the area under the curve, and that will tell us the displacement over that time period. So for number 2, the area under the curve, and this is for a v of t function, that will give you displacement or change in position, right? If we did the area under the curve for an acceleration graph, that would yield velocity. So there's one way to go from position, velocity, acceleration, find the slope. If you want acceleration, velocity, position, find the area. And we will just use simple trig formulas to do that. We're not going to get exact on these things because these are curves. It's very hard to find the area underneath a curve. So we're going to assume that they're squares and triangles. We won't even go into trapezoids. That's for calculus class. This is going to be our bridge into doing the power rule more. So what you will do to find displacement from t equals 4 to t equals 8 is we will find the area under the curve from this point to this point. Now, we need the area. Let's say that that is a square. It starts at 6, goes up to 8, and then goes right back down to 6. So let's say the height of this square is 7. Not perfect math, I know, and that's okay. This is the simplified version. But we will find the area of this square. The base, okay, area of the square, A of square. That is the base times the height, right? The base goes from 4 to 8. That's 4 seconds. 4 seconds. Then we multiply that by the rise, or by the height of the square, and the height is 7 meters per second, right? So if we multiply those, the seconds will cancel. That gives us just meters, which is the unit of displacement. 4 times 7, that means that the area of this square will be approximately 28 meters. So that means that from 4 seconds to 8 seconds, this object, whatever we're graphing the motion of, this object traveled approximately 28 meters. I'm not going to say it was exact because we kind of fudged the numbers on the curve, which is okay. Don't do that on your calculus AP test, but for now, until we get into more in-depth calculus, that's going to be acceptable as estimating using geometry. So 28 meters is the displacement from 4 to 8 seconds. Keep that in mind for the next problem. Next, what is the object's position at t equals 8 seconds? So how would we find that out? Well, first we have the displacement from 4 to 8 seconds. We know it traveled 28 seconds it traveled 28 meters in that time. Right? Now we need to know how far did it travel in the first 4 seconds from 0 to 4. Well, we can't estimate that using a square, so we will estimate that using a triangle. So the area of a triangle is 1/2 base times height. So we'll take 1/2. The base of that triangle is 4. The height of that triangle is 6. There's 6 times, no, let's say 1/2 times 4 is 2. 2 times 6 is 12. So it traveled 12 meters in the first 4 seconds. So let's say x from 0 to 4 was 12 meters. and then change in position from 4 to 8 from our last problem was 28 meters. Now, if we need to know what is the object's position at 8 seconds, we just add those suckers together. The position at 8 would be approximately 40 meters. And I'll go ahead and put a squiggle there just because we're not using exact figures right now. So it is approximately 40 meters. So using these techniques, finding the area under a curve or finding the slope of a curve, we can know just from this graph what was its acceleration at any given time by finding the slope of the curve at that point. And we can find out how far did this object travel over a certain period of time by taking the area under the curve. And we can find an object's position, assuming it starts at the origin, which the velocity starts at 0, so we can say that it started from rest. We can say that, we can find out wherever the object may be at any given time. We can find its position and we can find the displacement over a given time. So these methods, using the slope to go from position to velocity or velocity to acceleration, in calculus, you could use a derivative to do the same thing. Going from acceleration to velocity or velocity to position or displacement, you use the area under the curve. And an integral will do that. For now, we're just going to worry about derivatives. We're not going to do integrals right now, but let's get some more practice. So what is the area of an A versus T graph? So like we said before, area under a curve lets you go backwards from area to velocity, velocity to position. So here we can find an object's velocity using this information. So for the interval t equals 0 to t equals 5, what is the change in acceleration? Well, at t equals 0, the acceleration is 2 meters per second. At 5 seconds, the acceleration is still 2 meters per second. So on part A, the answer is 0. There is no change in acceleration during that time. So that means that it is constantly accelerating. It is speeding up from 0 to 5 seconds. Now, what is the change in velocity during that time? Well, let's take the area under that curve. It's not really curving, but under that graph. So we have the area, and we're going to use a square. So I don't have a whole lot of room to write here. Velocity will be the area of a square, which will be the base, 5 seconds, times the height, which here is 2 meters per second squared. One of those seconds will cancel with that s, and you get 10 meters per second. So over that time period, there is a change of 10 meters per second. Because it was accelerating 2 meters per second squared for 5 seconds. 2 times 5 being 10. So now what does the slope on acceleration versus time represent? Now remember, slope takes you from position to acceleration, and then position to velocity, velocity to acceleration, or slope, position, velocity, acceleration. But what happens if you take the slope of acceleration? Well, after that, you get what's called jerk. Jerk is the change in acceleration. Jerk is, I like to describe it as like when you're driving in a car, when you feel the car jerk. So for example, you are driving at a constant speed, or maybe you're accelerating, and then someone cuts you off, or a little bunny goes across the street and you slam your brakes on. Well, you had to jerk because your acceleration was either positive and then had to go negative, or it was constant and then had to go negative to slow down so you didn't hit the bunny. Don't hit the bunny. So jerk is the change in acceleration. That doesn't come into play a lot in this class. Actually, it comes into play 0 in this class, but it is important to know because it is a physical property that people use within physics. After jerk, there is also snap, which is change in jerk. There is crackle, which is change in snap. And there is pop, which is change in crackle. I don't know why they went full Rice Krispies on us after the jerk, but that's what we call it. So you can continue taking the derivative or finding the slope of graphs. However, eventually you will just hit zero. So for example, the acceleration here changes instantaneously at t equals 10, and then it changes instantaneously at t equals 15. There is no defined slope at that point, right? That slope you would say is undefined because it is straight vertical. So the jerk from 0 to 10 would be the slope of that line. Since it's flat, the jerk would be 0. Slope is 0. Then at 10, you have an undefined jerk because the acceleration instantaneously changed. It did not go through any transition that was measured. So then you have an undefined jerk at 10. Then from 10 to 15, you have a jerk of 0, constant acceleration. Acceleration isn't changing. Then at t equals 15, undefined jerk. Then you have a jerk of 0, constant acceleration from 15 to 20, and then at 20, right back to an undefined jerk as acceleration moves from -3 to 0. If jerk was kind of confusing, don't worry about it. You just need to know that slope can take you in one direction from position, velocity, acceleration, jerk, snap, crackle, pop. Now, if you take the area under the curve, that can take you the other way from pop to crackle to snap to jerk, and then to something useful, then acceleration to velocity to position. They go opposite directions, which is the answer to the bottom part there. Now, number 3, is there another way for slopes and areas to connect? Yes. So calculus equations, like the power rule, is how a slope and an area is going to connect. Now, the power rule that I glossed over and didn't give very much time to earlier is one of the foundational rules of taking a derivative. So a slope of a line is the same as taking a derivative of that function. Now, if you find the slope of a line across a time interval, you have essentially found the derivative across that time interval. If you find the slope at a certain point, you have essentially taken the derivative, the instantaneous derivative at that point. And then area is an integral. If you take the area under a curve, under a certain time frame, then you have integrated that function across that time frame. And now slope can take you, now this is going to get sloppy. Hang on, let me flip this over, resituate so I can write this in an easier way. Flip, flip, there we go. All right, so slope is position to velocity to acceleration and to jerk. Kind of a sloppy J. Then area does the opposite. You can start at jerk. That'll take you to acceleration, to velocity, then to position. Now, if the power rule kind of got you concerned or confused, don't worry. We're going to spend a lot more time before you're going to be expected to do much with that. But this is our calculus intro, where we are now starting the conversation that we can manipulate a graph to find these quantities, but it is more efficient to simply use a pattern like the power rule to find a function that describes the behavior of some of these properties across all time frames, not just the graphed time frame. So this is the start of our calculus discussion. We will do more of this as we continue through chapter 2, and that's why I'm keeping these videos a little short. But I recommend you go back, rewatch the power rule, and I would also recommend making up your own quadratic function, something that has t squared, t, and a integer without a variable. I recommend you make up some of your own quadratic functions and use the chain rule and get some practice with it, because the chain rule is going from position to velocity, velocity to acceleration, which is a very useful tool. Um, but next time we will definitely go more in depth on this kind of concept.